Hey everybody. Um, we have been talking for quite a while now about stars and their life cycle. So what can this tell us? Now that we've got a pretty decent handle on the full life story of stars, how are they born? How do they live? How do they die? What is their afterlife like? Um, Now we're going to start zooming out, and we're going to be doing this for the whole rest of the semester. Let's zoom out of what we've been talking about to see the bigger picture, and how can we use the small scale things like stars and their lives to get a handle on entire galaxies like our Milky Way. And then once we've got a handle on our galaxy, we're going to talk about other galaxies. And then once we talk about other galaxies, we're going to talk about the whole universe. So that's why I say zooming out to, from big things like stars to the biggest things like all of existence. That's the plan for the rest of the semester here. So, um, what are we talking about when we're talking about the Milky Way and our galaxy? When you look at when you look at the sky, especially in the summer is the best time to see the Milky Way because it's up overhead almost all night long in the summer. In the winter, it's a little harder to catch. But what is it? Well, on the face of it, to the naked eye, it just looks like this band of hazy, kind of milky colored light that stretches from one horizon to the other. Um, when telescopes were invented, people like Galileo looked into the Milky Way and they realized, oh, it's just made of more stars. That what you're looking at are, when you're looking into the glow of the Milky Way, you're seeing stars that are just a lot farther away, so that you can't resolve them. All of the stars that you can see with the naked eye, or with low-power telescopes, all the stars that you're looking at in the night sky are stars that are close to us. They are near the sun in our neighborhood of the galaxy. And that when you start looking at far away stars, the stars look so close together. Because we're looking at them so far away, they look so close to us. Sorry, they look so close to each other, rather, that you can't resolve one star from another. And therefore, you're just seeing the sort of diffuse glow of all of these stars right next to each other on our vision. So it just looks like one fuzzy, glowing path. This image on top here is a mosaic of the entire sky. So here, this top strip here is 360 degrees. From 0 through 180 to 360. You're taking the whole band of the celestial sphere and you're unrolling it like a map. And what you see is the Milky Way goes all the way around us, 360 degrees. It's brighter in one part and it gets darker and fainter 180 degrees away, but it's all around us, and all of these stars that you see are going away from us in all 360 degrees. If you were alive, about 100 years ago, right at the end of the 19th, beginning of the 20th centuries, people thought, well, hey, okay, so we live in this galaxy. First thing is, this is the only galaxy that we thought existed. When you look, here's a pretty zoomed out picture from a lower power telescope. There are a couple of other galaxies in this image. These two little blobs here are other small galaxies that are outside of our own galaxy. But when you look at them in an image like this, what do they look like? They're fuzzy and they're glowing, and they look kind of like nebulae. And so that's what people thought they were just nebula. So people thought, well, then the Milky Way and our galaxy must be the whole universe. That 100 and some years ago, they thought our galaxy, this disk of stars and gas and dust, is everything. And that there were these other nebula sort of, around our galaxy, but that's basically everything. Our galaxy is a fairly flat disk. What's it made of? It's made of stars and the interstellar medium. What's the interstellar medium? It's all the gas and dust floating out there in between the stars. What's keeping the galaxy together? Gravity, right? Everything that has mass exerts gravity. And so all of these stars and gas and dust, they're all pulling on each other, holding the galaxy together by their mutual attractions. And yeah, there are these, there's a few of these nebula around our galaxy. Let's see if there's another one in this. There's another one. Where are some others in this picture? That's probably one. People thought that was it. A little over 100 years ago, people thought the Milky Way is the entire universe. That's it. And that since the Milky Way, or since the Milky Way stretches away from us in all directions, well, then we must be near the center. We must be near the center of the galaxy. If this Milky Way goes all around us, then we must be near the center. And since the Milky Way is all of existence, since the Milky Way is the whole universe, our solar system must be near the center of the universe. Which should be setting off some red flags at this point in the semester, because human history is filled with us thinking we're at the center of the universe, right? We thought the Earth was the center of the universe. It turns out, oh no, the Earth isn't the center of everything. The Earth is going around the sun. And then people said, well, okay. So the sun is the center of the universe, and Earth and everything is going around the sun. So we're near the center of the universe. And then it turns out, oh no, the sun isn't the center of the universe, but maybe the sun is near the center of our galaxy. But the galaxy is the whole universe. Every time you come with some kind of observation that makes it look like you're at the center of the universe, red flags should be going off, because every time someone's made that argument in human history, they've always been proven wrong. And this time is no different, because here's a magnified view of one of those quote unquote spiral nebulae. This one is called NGC 281. When eventually the technology came about to measure the distances, how did they measure the distances to these galaxies? Well, they did it with things like Cepheid variables and white dwarf supernova. 100 years ago, the technology was getting there, right? Those women at Harvard were measuring the period luminosity relation of Cepheid variables, and Cepheid variables are pretty darn bright. You can find Cepheids in other nearby galaxies, and so when they did, they said, oh, great, we found Cepheids in NGC 281. I don't know that they did, for a matter of fact. I'm just saying, for example, what if they found a Cepheid in NGC 281? And they said, oh, okay, so let's measure the distance. And it turns out that these quote-unquote spiral nebulae, these things are way farther away than any other star. It turns out that the spiral nebulae are outside of our galaxy. And if they're a lot farther away than we think, then they must be a lot bigger than we think. How big are these nebulae? Oh, they're the size of our galaxy. So we're not looking. That's how they knew. By measuring things like Cepheid distances, they figured out those spiral nebulae are not nebulae. That they are entire galaxies of their own with billions and billions of their own stars. And all of a sudden, using something as basic as Cepheid distances, they realized our galaxy is not the whole universe. That there are many, many, many galaxies, and that we're not in the center. That all of a sudden the universe is a lot bigger, and those light sources are a lot farther away, and the number of stars in the universe are much, much, much larger than we used to think. that's why we've spent so much time talking about measuring distances before. Measuring the distances to things is not the most thrilling thing in astrophysics, but the implications for what they tell you, the conclusions that they lead you to, are revolutionary. And so you look at the spiral galaxy NGC 281. Once you realize that that light source is not a nebula close to us, it's a whole galaxy farther away than you thought, then you realize, well, wait, this thing here looks a lot. It's got this big glowing center, kind of like ours. It's got this dark dust lane running through the middle, just like ours, and it's about the same size as ours. Holy cow, that galaxy must be a lot like our galaxy. That our galaxy is not unique, that there are lots of other galaxies that look similar. Well, where are we in the galaxy? It turns out, when you look at this galaxy, for example, if we were living in the middle of that galaxy, or if we were living in the middle of our galaxy, a lot of these spiral galaxies have a big bright bulge of stars, a big bright ball full of stars in the middle. And if we lived in the middle there, if we lived in the middle of our galaxy, just like if we lived in the middle of this galaxy, just like if we lived in the middle of our galaxy, the sky would look radically different. There would be lots more stars, much closer to us. The nighttime sky would not be dark. If we lived in the center of our galaxy, nighttime would look just as bright as daytime, because there would be so many more stars so much closer to us. The apparent magnitudes would be so much brighter that there would be no darkness at nighttime. We must be living somewhere out here, right? This is a totally different galaxy, and yet this galaxy looks a lot like ours, and we can use these other galaxies to give us a hint at what our galaxy must look like. We can't get outside of our galaxy, right? We can't, because that would require traveling insanely large distances. We can't get outside of the galaxy to look back and see what the galaxy looks like. But we can use these other galaxies and compare and contrast how they look to how we look to draw some conclusions. And so you say, oh, well, this galaxy must look a lot like ours, and we don't live in the center because it's not that bright around here. We must be living sort of out here in the suburbs, right? We don't live in the big bright downtown of our galaxy. We live out in the nice quiet suburbs, and that explains why the sky looks the way that it does. Right? We live about here, and if you lived there in that galaxy, if you looked in that direction toward the center of the galaxy, what would you see? Well, you'd see a big bright ball of stars in the center with a lot of dust in the way. Big bright ball of stars, a lot of dust in the way. If you looked away from the center of that galaxy, there wouldn't be as many stars in that direction, which is exactly what it looks like looking over here and over here. Again, this is an all-sky map. This is the entire celestial sphere unrolled like a map. And so this is 180 degrees away from here. And if you look directly away from the center of the galaxy, yeah, there's stars in that direction, but not nearly as many. And if you looked north or south of the plane of the galaxy, then you'd look north or south, and there wouldn't be as many stars in that direction. So this is how we get a sense that, oh, okay, now that we've got better telescopes, now that we've got better cameras, now that we can get a better map of the sky as we see it, and now that we can look at these other galaxies and compare and contrast them with us, now we know we don't live at the center of the galaxy. We live off in the suburbs, and when you're looking in this direction in the sky, this direction in the sky, by the way, is toward the constellation Sagittarius. So when you're looking toward that big bright part of the Milky Way in the direction of Sagittarius, you're looking toward the center of the galaxy. And if you're looking 180 degrees away from that, most of that is in the direction of Orion. If you look toward Orion, the sky is darker, the Milky Way is darker, because you're looking away from the center of the galaxy where there aren't that many stars in that direction. And you say, but Brian, like, Orion is a big constellation with a bunch of bright stars, right? You got the belt of Orion, you got Betelgeuse, you got Rigel, right? There's a bunch of bright stars in Orion. And I say, yes, because those are close to us. Right? The Milky Way, all of those faraway stars, is darker in the direction of Orion. And all of the bright stars that you can see in Orion, those are near us. Those are close to the solar neighborhood, which is why they look so bright. Turns out that galaxies like ours are not uncommon. There's a lot of spiral galaxies where you've got this disk, this extended disk of stars with spiral arms, this big bright bulge of stars in the center, and uh, and a lot of dust, that would block your view if you lived in that galaxy. So we can't see, what does our galaxy look like exactly? Does it look like this, or does it look more like this, or does it look more like this guy here? That's very hard to do because, again, you can't we can't send a camera outside of the galaxy to take a picture of a bird's eye view. I mean, I guess we could try and do that, but it would take the space probe many millions of years to get out there, and then it would have to the equipment would have to stay alive that long, and then it would have to send the message back to us, and there would have to be people to see it. It's not going to happen. So when we take a picture, sort of this picture that I showed you here at the beginning, this is a map of what we think the galaxy looks like based on the data that we have, right? Because here we're living here in the suburbs. Again, there's the big bright downtown. When you're here on Earth looking into the galaxy, you can see, oh yeah, there's lots of stars in this direction and lots of stars in that direction and not as many in this direction. So there must be an arm here and an arm there and not an arm there. And then there's the bulge in that direction. So this is not a photograph. This is a map based on the observations of stars that we actually do see. But because there are lots of these spiral galaxies out there, we don't have to get outside of our galaxy and look back. We can just use these other galaxies and say, well, how are they like ours? How are they not? In order to reconstruct that map like we just looked at. To understand what's going on in galaxies, let's put that story together that we were talking about last time about the lives and deaths of stars. Because every galaxy is undergoing a giant recycling program. What happens in a galaxy? Well, you've got gas floating around there in the interstellar medium. Eventually that gas cools off and gravity pulls it together so that you get those cold, thickening molecular clouds. Eventually those molecular clouds start clumping up and collapsing and forming new stars. Those stars live out their life cycles, living on the main sequence, taking hydrogen, fusing it into helium, and then eventually taking helium, fusing it into carbon, and then even heavier elements, right? Eventually, when those stars die, they return most of that gas back into the galaxy, right? When a star dies, what happens? Well, if it's a low-mass star, the outer layers blow out as a planetary nebula, which is what you got there, right? Here you got this bubble of gas. That's a planetary nebula blowing away from a white dwarf. Or in the case of a high-mass star, what happens when high-mass stars die? They blow up and go supernova. So whether it's a planetary nebula or a supernova, most of the gas that made up the stars blows away and it gets mixed back in to the interstellar medium again, so that gas can be recycled into the next generation of stars. Right? Every galaxy is undergoing this giant program, this giant recycling program of taking gas, turning it into stars, and then when those stars die, it turns back into gas again. And then that gas can be remade into the next generation. What's different, though, with the next generation? As you go from one generation of stars back to gas and then into the next generation of stars, what is different about the next generation of stars? And the answer is their metallicity. Because while those stars are alive, what are they doing? Those stars stay alive by taking light elements and fusing it into heavier elements. Helium, carbon, oxygen, neon, sodium, all the way to iron, and then, in the case of the supernova, iron all the way to uranium. So that when those stars blow up and that gas gets returned to the ISM, the interstellar medium is enriched in the heavy elements that got created while the stars were alive, and the heavy elements that were created while the star was dying. And then that gas that gets recycled into the next generation of stars, those stars are also more enriched in heavy elements. And so by looking at the metallicity of stars, by looking at what is metallicity, remember, metallicity is how enriched a star is in metals. What are metals? Metals are any element heavier than helium. So every star, remember, every star is mostly hydrogen with a lot of helium and a little bit of metals. But that little bit of metals changes over cosmic history. And so you can look at the metallicity of stars and you realize there have been 3 major epochs of star formation. There have been 3 major generations of star formation in the history of the universe. And for historical reasons, for weird historical reasons, we actually count backwards in time. So that the sun is a population 1, the generation before the sun is population 2, and then the third generation is population 3. Sorry, I should say the first generation is population 3. So it's a little bit backwards, okay? So go with me here. Right after the Big Bang, right after. Okay, so like 700 million years after the Big Bang. So the Big Bang happened. When the Big Bang happened, the only elements that were created were hydrogen and helium, and a tiny, tiny bit of lithium, but that's it. The only elements that existed after the Big Bang were hydrogen and helium. And so everything was gas. After about 700 million years, the universe cooled down enough that gas could clump up and start giving birth to stars. And so that very first generation of stars, right after the Big Bang, are called population 3. And you know you're looking at a population 3 star if it has no metals, because no metals existed at the time, right? There were no metals that existed in the universe. So if you find a star with 0 metallicity, you know that must be very old. It was formed right after the Big Bang. Or, 700 million years after the Big Bang, which might as well have been right after the Big Bang, in the grand scheme of things. Those stars lived. A lot of those stars died. And when those stars died, when those population 3 stars died, they created, during their lives and during their deaths, they created the first metals in the universe. So the population 3 stars died, they blew up, or they blew out as planetary nebula, and they created the first metals, the carbon, the oxygen, the iron. But they only made a little bit, because there weren't that many stars yet. And so about 10 billion years ago was the peak in the second generation of stars. Eventually, the second generation of stars was born. We call those population 2 stars. And population 2 stars were born with a little bit of metals. Right? So when you look at a Pop 2 star, you know it's a Pop 2 star. You know it's an old star if it's very low metallicity, because it only has the metals that were made in Pop 3. There are not that many population 3 stars still around. Or if there are, we have had a really hard time finding them, because the population 3 stars were born like over 13 billion years ago. A lot of those stars are dead already. So it's very hard to tell if you find a star with really low metallicity, or no metal, or, insanely low metallicity. There are a few stars that have been found that have really, really low metallicity. And the question is, okay, are they Pop 2 stars, or are they Pop 3 stars that have just been contaminated with a little bit of metals? I kind of err on the side of the latter. Take this with a grain of salt, because I could very well be wrong about this. There are a handful of stars that have been found with minute amounts of metals. There's just a little bit of carbon in the spectrum of that star. And if it's got low metals, then the default is to say, well, that's a population 2 star. But population 2 stars are low in metals, but these stars that I'm talking about are even lower than that. And I kind of think, again, this is just me here, but I kind of think that some of these stars are probably population 3 stars that were just contaminated by supernova dust after they were born, and that's why there's a little bit of metals. I could be wrong though. Maybe they are pop two stars. This is still an open question. We have never found a star that has no metals. What I said a minute ago is what I said a minute ago about if you find a star with no metallicity, it must be pop 3. It's true, but notice I said if you find a star, because no one has found a star with 0 metallicity. Is that because all the pop 3 stars are dead already? Maybe. But remember, low mass stars should live for a very long time. Low mass stars live for hundreds of billions of years, and the universe isn't hundreds of billions of years old. There should be some pop 3 stars still alive. Maybe some of those insanely low metallicity stars are pop 3 stars. They were born with no metallicity, but then some other stars went supernova near them later on, and that supernova nucleosynthesis, the elements that were made in the supernova kind of got dusted onto the surface, and so now there's some carbon absorption or some oxygen absorption in the spectrum of the pop 3 star. It's possible. Or maybe not. Maybe these are just population 2 stars that really have a very low metallicity. This is still an open question. The peak in population 2 was, like I said, about 10 billion years ago. There are still a lot of population 2 stars still alive. We see them in the galaxy pretty easily. A lot of those population 2 stars, they were born, they lived their entire life cycle, they died. When those stars died, they blew up and they created even more metals. And then, about 5 billion years ago, that gas got recycled into the 3rd generation of stars. The 3rd generation of stars are what we call population 1, and this is stars like the Sun. So you're looking at a population 1 star because it's got fairly high metallicity. Why does it have more metals? Because those stars were born out of gas that was enriched by the metals created by 2 previous generations of stars. Pop 3 made metals, Pop 2 made metals, and all those metals not all of them, but those metals got reborn into population 1, and so that's why there are stars like the Sun that are fairly high metallicity. Also, that's why you and I are here. Right? We are here because our bodies and the Earth that we're standing on are made of metals. They're made of silicon, oxygen, iron, nickel, carbon, calcium, aluminum, right? You and I could not be here 10 billion years ago because there weren't enough metals in the universe to give birth to rocky terrestrial planets with sophisticated organic chemistry on them like the Earth. We need 2 previous generations of star formation. We need to be a 3rd generation star. We would need to be orbiting around a 3rd generation star in order for terrestrial planets with life on them to evolve. So there's a reason why you and I are here in a universe that is 14 billion years old. But that was 4.5 billion years ago, right? The sun was born, our solar system was born 4.5 billion years ago. A lot of Pop 1 stars have died by now because very high mass stars don't live very long, right? So there are stars being born today that are going to be even higher metallicity than the Sun. What do we call those? And this is where the astronomical community hasn't quite come to a consensus yet. The stars that are being born today are high metallicity, and so a lot of people say, well, they're high metallicity, so we'll just call them population 1. We'll lump them in with Pop 1. There are other people that say, well, no, these are a distinct different generation. We are in the midst, stars being born today, they argue, are part of the 4th generation. of stars to be born. So we should, since we're counting down 3, 2, 1, we should call these stars population 0. Or maybe we'll call them population 0.5, which, I don't know, seems like a little too clever by half if you ask me. Um, you know, th- we haven't really come to a decision about what we want to call these things. But they are high metallicity. Stars born today are also high metallicity, like population 1. So, pop 1, pop 0, whatever you want to call them. The easiest place to find population 1 stars are in open clusters. So there are two types of star clusters that you find in the galaxy. What are called open clusters and globular clusters. So we'll get to globular clusters in a second. But the Pleiades, we've looked at the Pleiades before this semester. The Pleiades is an open cluster. Why is it called an open cluster? It has to do with the shape. Open clusters don't really have a symmetrical, well-defined shape to them. They really don't have a geometry to them. Open clusters tend to be sort of irregular, and the stars are in random places. Why? Because these are young stars. Open clusters are full of young stars. These are stars that are just born out of the gas of their star-forming region. And so, since the stars are born in fairly random locations, then when you look at newborn young stars in open clusters, they tend to be in fairly random locations all over the place. So that's why they're called open clusters, because they don't have a closed shape to them. They're sort of open, and the stars are allowed to go out in the random directions that they were born in. So, open clusters are population 1 stars. They're young. These are fairly newborn stars in the grand scheme of things. What color is an open cluster? It's pretty blue, right? Why? Is this cluster blue because all the stars are blue? I mean, if you squint and look at the picture, you can tell. No. Remember the initial mass function. Remember how stars are born. When stars are born, you never just get all blue stars or all red stars. When stars are born, they're born according to the initial mass function, where you have a small number of high mass stars, a larger number of medium mass stars, and a large number of low mass stars. What color are low mass stars? They're redder, right? There are hundreds of stars in the Pleiades. Probably actually more like a couple thousand stars in the Pleiades. And yet, what kind of stars are the most common in a population of young stars? What does the initial mass function say? What kind of star is going to be the most common star in this cluster? The initial mass function says the most common star should be the low mass star. What color are low mass stars? They're the redder ones. In this cluster, the red stars are the most numerous. And yet, what else do we know about those red low mass stars? They're pretty low luminosity. In this cluster, in all open clusters, the hot blue high mass stars are the rarest. And yet, what do we know about high mass hot blue stars? They also have very high luminosity, right? This is the funny thing. This population is pretty blue. Is that because the blue stars are the most common? No, the blue stars are the rarest, but the blue stars are also so luminous. These stars, those handful of high mass blue stars, they overwhelm the brightness, they overwhelm the luminosity of the cluster, so it makes the whole cluster look blue. Not because the blue stars are common, but just because they're really bright. The most common stars here are the red stars, and yet those red stars are so dim they don't really show up next to the bluest, brightest O and B stars. Why do you have open clusters? Because that's where the stars are born, right? Here's the Eagle Nebula, We were looking at this before with star birth, right? Here's the Eagle Nebula. There's those famous pillars of gas where there are new stars being born inside the nebula, and yet there's a cluster of stars, right? These are the bright O and B stars that are shining their light onto those pillars of gas and making the gas evaporate, right? All of that hot ionizing radiation given off by the O and B stars are what's lighting up all of this gas and making it glow. Eventually, what's going to happen, right? When stars are born, they're born in these clusters, surrounded by all of the gas. And then eventually what's going to happen is all the gas will blow away. Just like we saw in the star birth lecture. All of the gas in this star forming region will eventually blow away, either because it's heated up by the gas, rather the gas is heated up by the stars and it blows away, or the stars go supernova and they explode and blow the gas away. Either way, whether it's by radiation or supernova explosions or whatever, eventually all of this gas is going to blow away, and all you're going to be left with is the stars that got born before the gas got blown away. And so eventually the gas evaporates away, and you've got a cluster of stars, an open cluster of young, newborn stars left together. For a while, right? Open clusters don't tend to last that long, because you've got all these stars. Let me go back to the Pleiades here real fast, right? You've got a few thousand stars. They're all pretty close together, but all of these stars are pulling on each other's with their mutual gravity. But it's not going to stay together forever. These stars all have their own velocities. They all have their own momentum. And there isn't enough mass in this cluster to keep the cluster together. Eventually, these stars wander away, this group of stars breaks up, and all the stars settle into their own separate orbits around the galaxy. So if you find an open cluster like this, or like this, or like this, when you see an open cluster, you know it's young because it's blue. How do you know this cluster is blue? You know it's blue because you look at it. How do you know this cluster is young is what I was trying to ask. You know this cluster is young because there are still some blue stars around. Because what else do we know about these blue stars? Those blue stars are high luminosity. Why are they so hot and so bright? Because they're high mass. What else do we know about high mass stars? They don't live very long. So we know this open cluster. We know the Pleiades is full of young stars because all of these stars are the same age. They were all born out of their star-forming region at the same time. And we know that this cluster of stars is young because if this cluster were any older, those blue stars would be dead by now. You can look at a population of stars and you can get a handle on how old it is by looking at the color. The younger the population of stars, the bluer it's going to be, because if it were older, the blue stars would already be dead. You can't do this for individual stars, right? This is careful. You can't look at a single star and know how old it is, right? You can't just look at the sun and say, oh, how old is the sun? Because the sun is going to look like a yellow main sequence star for the better part of 10 billion years. So if you were an alien looking at the sun, you can't just look at the sun and go, oh, it's a yellow main sequence star. It's 1 billion years old, or 5 billion, or 9 billion, because the sun is pretty much going to look the same for that whole time. So you can't just look at a star and know its age individually. But if you look at a population of stars, right? A population of stars like a cluster where all of these stars were born together, they were all born out of the same star-forming region, they're all the same age, you can use the color of that population of stars to get a handle on the age. The bluer it is, the younger it must be. The redder it is, the older it must be. Where do you find open clusters in the galaxy? Well, you find them mostly in the plane of the galaxy. When you look at our galaxy and you map out where are the open clusters, They're in the disk. They're in the plane of the galaxy. Why? Because open clusters are full of young stars. What are young stars made of? They're made of gas, right? Young stars are made of gas and dust. Where is the gas and the dust? The gas and the dust is in the disk of the galaxy. You don't find open clusters up here and down here. You find them in the middle of the galaxy. That's where young stars are. That's where open clusters are. That's where the star formation is happening. And so when you're looking at our galaxy, right, there is stuff north and south of the plane of the galaxy. You can see it up here, down here, but that's not where you see the open clusters, right? You see the open clusters in the plane of the galaxy, and they're all moving in the same direction. The disk of our galaxy is all rotating in one direction, counterclockwise in this cartoon, and it's all rotating. All of these stars and gas, everything is orbiting in the same direction at about 200 kilometers per second. Our sun and the whole solar system is orbiting around the center of our galaxy at about 200 kilometers per second. Which sounds pretty fast, except that the galaxy is so big that it takes our solar system about 220 million years to complete one orbit around the center of the galaxy. And, 200 million years, that sounds like a really long time, except that our solar system has been around for 4.5 billion years, which means that in the whole history of our solar system has orbited the galaxy something like 16 or 20 times since our solar system formed. The other kind of clusters are the globular clusters. The globular clusters are old. They are population 2. They're low metallicity, but they're big. These globular clusters tend to be 100,000 to 1,000,000 stars, all fairly close to each other. This globular cluster, they're called globular clusters because they are globe-shaped. These are spherical balls of stars. Oops, sorry about that. All right, so they're called globular because they're shaped like a globe. It's a spherical clump of stars, and this particular one is called Omega Centauri. It's 12 or 13 billion years old. But what you're looking at is a cluster of 1,000,000 stars. You are looking at 1,000,000 of something. How often does that happen? Where you get to look at something and say, oh yeah, there's 1,000,000 of something right there. But that's what you're looking at. It doesn't show up so much in this picture. If you look more carefully, if you zoom in on one of these globular clusters, the population of stars tends to be fairly, not reddish, but, kind of yellowish. Yellowish orange. And so, like I said, why is this globular cluster so yellow? Is it because there never were any blue stars? No. There used to be lots of blue stars in this cluster. They're all dead. And then there were a lot of white stars, and then they died. This group of stars, an old population of stars, is redder not because there never were blue stars, but because all the hotter, bluer, higher mass stars are already dead, and so the only stars left in an old population of stars, the only stars that are left are the ones that live a long time. And what color are the long-lived stars? They're redder. And so you don't tend to find globular clusters that are like red, but this one especially is kind of a yellowish orange. You notice from this, not an animation, this is an actual series of images here. You've got a bit of a GIF going on here, where you'll notice, because these clusters are so full of stars, right? Back in the population 2 era, you could make star clusters that were hundreds of thousands of stars because there was a lot more gas around back then. So you could make, right? These days in population 1, you find open clusters that have thousands of stars. Back 10 billion years ago, there was so much gas available that you could give birth to clusters that were hundreds of thousands of stars. And also, because you've got so many stars all together, you can look at these stars, those stars. There are some of those stars are variable stars, and some of those variable stars are Cepheids. And so you can figure out the distances, and you can map out where are the globular clusters, because you not only know where the globular clusters are in the sky, but you know where they are in three-dimensional space, because you can use these Cepheid variables to figure out their distance. So where do you find the Cepheids? You find them all over the galaxy. You find them in the plane of the galaxy. You find them north. You find them south. These globular clusters are orbiting in random orbits, all orbiting around the center of the galaxy. So this is where, out here in what's called the halo, the outer layer of our galaxy is called the halo of the galaxy, where you find some stars are going clockwise, some stars are going counterclockwise, and the clusters are going in random directions. They're all going in random directions, orbiting around the center of the galaxy, and the halo is where you find old stars. Right? In the disk of the galaxy, you tend to find younger stars, because that's where stars are born. Stars are born in the disk of the galaxy. And so if the stars are still young, they're going to be near where they were born. But as stars get older, globular clusters, as stars get older, they might be born in the disk, but they can settle into orbits that lead to being further north or further south of the galactic plane. And so stars can settle into orbits that let them wander up into the halo. This takes a very long time, though. And so you find these stars in the halo, you find older stars, redder stars, fainter stars, because older and redder means fainter, typically, on the main sequence anyway, and also globular clusters. So, if you want to find, what does this all add up to? What this adds up to is population 2. You want to find a population 2 star, look in the halo of the galaxy. You want to find a population 1 star, you look in the disk of the galaxy. Like I just said, right? The disk of the galaxy is where you're finding the active star formation. Why? Because that's where the gas is, right? You need gas and dust to give birth to new stars, and you need star formation to give birth to open clusters and young blue populations of stars. So that's where do you find all that? You find all that in the disk. There's a third component of the galaxy, and that is that central bulge. It is hard to see the bulge of the galaxy in the visible spectrum because there's all that gas in the way. This picture is a mosaic of the entire sky. So here is the entire celestial sphere, unrolled like a map again. But this is the galaxy in the infrared. And since you're looking in the infrared, you can see through a lot of the gas and the dust, and you can see all the way across the galaxy to the center of the galaxy. And when you look toward the center of the galaxy, there's that bright bulge at the center. And so what is the bulge made of? Well, the bulge at the center of the galaxy is a big ball of stars, but it's a mixture of young and old stars. Right? The disk of the galaxy is mostly young stars. The halo is mostly old stars. The bulge is a mix of young and old. And also a little bit of gas and dust. So when you add all this together, when you add up the disk and the halo and the bulge, what do you get? Well, you get a galaxy that is... I wrote this out as like the range, but most of the recent measurements sort of tilt the measurement toward the upper side. So the number of stars in the galaxy is more in line with 400 billion stars. It's closer to 800 or 1,000 billion solar masses. What's the age of the galaxy? This is hard to say. You can't just look, you can look at a population of stars and get a handle on the age from the color, right? Young means blue, old means red. But a galaxy is a collection. And so, how old is a galaxy? Basically, what you're asking is, well, a galaxy cannot be younger than its oldest stars. So how old is our galaxy? Well, our galaxy has some 13 billion year old stars, so the galaxy is probably something like 13 billion years old. But the galaxy also has some younger stars in it, like the sun, and also like the population zero or whatever you want to call them, right? The stars that are being born right now. How big is the galaxy? Well, a nice round number is that our galaxy has a diameter of about 100,000 light years in diameter, but it's got a little bit of thickness to it, so it's like 2,000 light years thick. The disk, anyway. The halo gets to be much bigger. What about those spiral arms? Why does the disk have those spiral arms? The funny thing is, the spiral arms of a galaxy are not rigid objects. An arm is not one solid thing and all of the stars move together. No. All of these, the disk of a galaxy is just stars and gas. All of the stars are moving in their own orbits around the center of the galaxy. So then why does the disk have arms to it? And the answer is because, well, the arms that you can see are bright. Right? Let's see. What do you find in the spiral arms? Well, you find these dust lanes. What do dust lanes tell you? Well, that must be where the gas in the dust is thicker. If the gas is thicker, then the gas is going to have an easier time collapsing. What happens when gas collapses? You have star formation. So you also, in the spiral arms, you also find those red blotches. What do those tell you? Those red blotches are H2 regions. I've got pictures here. Let me flip ahead here, right? When you look at a galaxy and you see those red blotches, you say, aha, that's a star-forming region. That's an H2 region. That red blob is hydrogen glowing because it's being heated up by newborn high-mass O and B stars. Then what else do you find in the spiral arms of a galaxy? Well, you find a bunch of blue light. What's giving off the blue light? Blue stars. A blue group of stars is a young newborn group of stars. So the reason why galaxies have spiral arms is that the spiral arms are waves. They're like waves on the ocean, right? A spiral arm is a wave of density in the gas and the stars and the dust. You can kind of here's a bit of an analogy. You can kind of think about a spiral arm as being sort of like a traffic jam, where when you have an accident on the road, things clump up, things bunch up, right? You want to avoid the traffic, and so everything slows down. And when all the cars slow down, they get closer to each other, and so therefore you have this area where the cars are driving slower and they're being denser, right? They're closer to each other. They're condensed. That's pretty much what's happening in the spiral arms. In the spiral arms, the reason why those spiral arms are brighter is because the stars are closer together and the dust is closer together. And therefore, since the dust and the gas are getting closer together, you're having new star formation. New stars are being born. And if new stars are being born, then you're going to get a lot of new light from all those new young blue stars. And therefore, the spiral arms tend to glow blue. The funny thing is, yes, the spiral arms are moving. The spiral arms are orbiting around the center of the galaxy. But the spiral arms are not moving as fast as the stars are. You can actually watch, albeit very, very, very slowly, you can see stars move into a spiral arm, slow down, and then When that material slows down, it clumps up, it gives birth to new stars, and then new stars and the old stars are seen leaving the spiral arm. So basically, that's a bit of a complicated explanation. What am I saying here? What I'm saying is the spiral arms are just a wave where things get dense, they clump up and they slow down before they keep on moving. You can watch and stars will move into the spiral arms, slow down, and then move out again. So the reason why these spiral arms are brighter is because the stars are closer together, and also new stars are being born. And most of these bright new stars, right? You get these bright, new, blue, high mass stars. These high mass stars don't live that long. Remember, those high mass stars only live for a few million years, which means in here, in this dark dust lane, you're seeing all these red blotches of new star formation. Then out of the dust and the red light, out come a wave of bright blue, young, new stars, and then they die. Those stars don't live long enough to orbit the galaxy one time. The reason why you have this wave of bright light and then it gets dark over here is because by the time the stars get over here, the only stars that survive are the dimmer ones. All of these bright, hot blue stars die fast, and so you end up with this gap here. The space in between the arms is darker because are there stars in there? Yeah, there's stars in between the spiral arms, but not the brightest of the bright stars because those ones are already dead. So the spiral arms are not rigid objects that are spinning around the galaxy like a frisbee. They're just ripples. The spiral arms are just ripples in the waves, in the density of the stars and the gas and the dust. I kind of already explained this. I don't need to say this again. Right. And so what you see coming out of the spiral arms are new stars, right? When you look at a spiral galaxy, when you look into the spiral arms, you're going to see the dust lanes of condensed gas and dust. You're going to see the red blotches from H2 regions. You're going to see new blue stars being born and coming out of the arm. And then there's the gaps in the wave. From one wave to the next. There's the gap where there are still stars orbiting around the galaxy, but the stars are more spread out because now they're allowed to speed up, just like cars leaving an accident, right? Once you leave an accident on the highway, you speed up again and the cars space out more. Same thing is happening here. There's those dark areas in between the arms where the stars are moving faster. They're not the brightest stars because those are already dead, and the stars spread out. They're farther apart from each other, so that the average brightness in that area is less because there's fewer stars. There's fewer stars per square parsec, you could say. What causes the traffic jam in the first place? Right? Why do I say, oh yeah, there's a ripple in the galaxy, there's a traffic jam in the stars. What causes this traffic jam in the first place? And the answer is collisions. When two galaxies crash into each other, the stars and the gas tend to crash into each other and clump up, and that clump becomes a new spiral arm. Our galaxy hasn't had a major collision between, another galaxy crashing into us in a long time. But we have had a bunch of dwarf galaxies crash into us. There are those two little those two little galaxies that we were talking about at the very beginning of the talk. Those are not full-size galaxies. Those are what are called these little guys are what are called dwarf galaxies. They are smaller. They're closer to us because these two galaxies are orbiting around our galaxy. And they are sooner or later going to crash into our galaxy and get gobbled up. but the gravitational pull between that galaxy, the Large Magellanic Cloud, and our galaxy, that those gravitational pulls yank the stars and the gas around and cause the stars and the gas to clump up. And every time the stars and the gas clump up, when the gas clumps up, you get a burst of new star formation and you've got a new spiral arm. And it works both ways because gravity is a force, and for every force there's an equal but opposite force. So when we zoom in, here's a close-up look of the Large Magellanic Cloud, and the Large Magellanic Cloud looks all twisted up. If you look at the gas in the LMC especially, it doesn't look like a nice, pretty, symmetrical galaxy like the Milky Way. You've got this big bright bar here. There's an arm twisted up going this way. There's another arm twisted going down this way. And you've got all kinds of star formation. Again, look at the red blotches. Look at the H2 regions. There's star formation going on all over the place, especially in the Tarantula Nebula. This big bright blotch here is a huge star-forming region. Much bigger than the Orion Nebula or the Eagle Nebula. The gravity of the LMC, the Large Magellanic Cloud, the gravity of the LMC is pulling on the Milky Way, and the Milky Way is ripping apart the Large Magellanic Cloud, pulling it, yanking it, twisting it, and causing the gas to clump up and collapse and form new stars. The fact that our galaxy has a bunch of little arms, right? Our galaxy does not have two big spiral arms like M51 here. This is M51, right? Our galaxy, where's that map? There we go, right? Like I said, this is a cartoon, right? This is not an actual photograph, but this is a map based on real measurements. Our galaxy does not have two big arms. Our galaxy has a multitude of little spiral arms. Each of these spiral arms is probably made by a collision. Some other small dwarf galaxy wandered a little too close to our galaxy, and our galaxy's gravity grabbed it and gobbled it up. And when those two galaxies collided, they smushed together and created a new spiral arm. And because our galaxy has a bunch of little spiral arms, we can bet that our galaxy has cannibalized lots of little dwarf galaxies over and over and over again over the last few billion years. We haven't done it to the Magellanic Clouds. The large and small Magellanic Clouds haven't been ripped apart and gobbled up by our galaxy yet, but it'll probably happen in another 1 or 2 billion years. Galaxies crash into each other a lot. And this is probably why. When galaxies tug on each other or crash into each other, when two galaxies interact and their stars pull on each other, you create those density ripples, you create the spiral arms. And the fact that there are lots of spiral galaxies with lots of spiral arms means that galaxies are crashing into each other and eating each other all over the universe all the time. And it's been happening for the whole history of the universe. Our galaxy is not unique in cannibalizing and eating up and assimilating the stars and the gas of other galaxies. Happens all the time. This is where large galaxies come from. Right after the Big Bang, when the universe was just gas and the gas was starting to clump up and give birth to the first generation of stars, right after the Big Bang, all galaxies were small galaxies. But then those galaxies crashed into each other and got bigger. And then they ate up another galaxy and got even bigger, and ate up another galaxy and got even bigger. So that after 14 billion years of this, you end up with large, massive galaxies with hundreds of billions of stars like the Milky Way. The whole history of the universe has been filled with small galaxies crashing into each other to become bigger and bigger and bigger until today our galaxy is a pretty darn big galaxy because it has eaten lots of smaller galaxies to get that way. Okay, so studying the Milky Way has its pros and cons. right? The downside of studying the Milky Way is we can't get outside of it, right? We can't look at the galaxy from the outside in. We can't get a bird's eye view of the Milky Way the way we can get a bird's eye view of of the Large Magellanic Cloud or of M51, right? Um, we have to stay inside of our galaxy and then try to look out at it. It's kind of like, I mean, it's very much like losing the forest for the trees, right? If you're in the middle of a forest, to get to a real picture here, right? If you're in the middle of a forest and somebody says, well, how big is the forest? Well, I don't know. I just see trees in all directions, right? Well, where's the edge of the forest? I don't know. All I see is trees in all directions, right? That's what studying the Milky Way is like. We are inside of our galaxy, looking out at it, trying to figure out where is the edge. And it's a lot easier to do in the infrared than it is in the visible, but even here, not easy. The upside of looking at other galaxies is that we can look at them from the outside in. We can look at the bird's eye view of M51 or these other galaxies. The downside is that these galaxies are so far away that they're not as close and they're not as easy to see. So we can learn a lot about our galaxy from studying other galaxies, ones that we can look into from the outside. The reverse is also true. We know a lot about other galaxies because we've studied the stars and the gas and the dust inside of our own galaxy, right? By studying nearby stars and being able to put together the life cycle of stars, we can then zoom out to look at all these other faraway galaxies and say, oh, I've got a pretty good idea about what's going on in that galaxy because I know how gas turns into stars, stars go supernova, and they create more dust to be born into the next generation of stars. We can do this both ways. We can take the nearby to figure out about the far away, and we can look at the faraway galaxies to learn about our own backyard. And that's why the next thing we're going to talk about is what do we see when we study other galaxies. So that'll be next time. I hope you're all doing well, and see you then. All right, bye.